Okay, cool. So we'll just resume with the multi-step synthesis problem that we left last time. So in this one, I'm giving you all the reaction intermediates and you have to give me the reagents used. So who wants to start? In reaction A, what's happening? Yeah, so what reagent do we use for epoxidation? Yeah, and MCPBA is a type of, yeah, true. It's a type of peroxy acid. Okay, and then in B, what do we do with the epoxide?
We break it.
Yeah, and then can you tell which side we broke it on?
The left side.
The left side, yeah, why?
Back side of the car.
Yeah, and then how can we tell?
Because it is trans.
It is trans, but how did it get to be trans?
It's gonna be sitting around. Huh?
Yeah, because what?
Yeah.
It's SN2, so we had a word that starts with I and ends with version. Yes. So we saw that this carbon got inverted, so we know that's where we did the SN2 attack. And this carbon is the more or less substituted side. And since the nucleophile attacked on the less substituted side, did we use an acid or base catalyst?
Base.
Yeah. Yeah, sure. And then usually it's like over water or something. That's it. Okay, and then for C, what happened?
Oxidation.
Yeah, and why didn't this alcohol get oxidized? This one?
Because it wasn't, the reagent wasn't as strong.
And anyone else have thoughts?
Okay.
Yeah, it's tertiary. You can't oxidize or reduce tertiary things. So we went from a secondary alcohol to a ketone, right? What reagents can do that? NaH? Is NaBH4 reducing or oxidizing? So that would take us the opposite way. Yeah. Either one, right? Because it's a ketone. So you can use weak or strong with the ketone. So yeah, we can go with KMNO4. And what is KMNO4 usually over? Yeah. Cool. And then in D, what happened? Is it?
Yes.
Yeah. So what Grignard reagent did we use?
Magnesium propane.
Um,
bromine.
yes, we used
Oh, never mind.
we used a butane with, you're right, an MGBr attached to it. Wait, is that a but? Yeah. So we have that. And then when it added, oh, okay, I never mentioned this, and Roche like did his weird like orbital diagram. So basically the stereochemistry you're gonna have when you attack a carbonyl is that the substituent or the nucleophile is, it's added, what do you call it? Wedged, and then the carbonyl becomes dashed. And that's due to like the orbital geometry.
Is it always gonna be
Um,
dash, or just doesn't matter, it has to invert either way?
I think it's usually written as like, I don't know.
You could attack either side.
It doesn't, yeah, it doesn't matter that much. But the way he drew it was like this.
What solution would it be?
Oh,
Oh, yeah.
it would be in a solution of ether, but then the second step of the entire reaction would have to be water or something. So you could do like MGBr over ether, and then step 2 would have to be like H2O to pronate it. Okay. And then where else did we leave off?
Wait, I have a question on that question that we just did.
Okay.
How do we know on this, on B, how do we know when we go into the next sentence that it was?
That it was base catalyzed.
Well, yeah, how do we know that?
So if you have an acid catalyzed, it attacks at the more substituted side. So if it was acid catalyzed, we'd have an inversion at this carbon. So the alcohol would be dashed and then the CH3 would be wedged. But it stayed the same, so we know we attacked the other side. And the other side is less substituted. Bases attack less substituted sides.
What would the solution be for MCPBA?
Oh, I don't know. I've never seen an over solution.
So it won't be on the test maybe, or?
I mean, if it is on the test, like you won't get the answer wrong because the solution is like the wrong one. Like he won't give you MCPBA over two different things. You have to pick the right one.
All right.
Without oxidation, which reagents are the stronger one?
KMNO4 and then the H2CrO4.
HCl4, that's stronger.
Yeah.
that's good. All of the chromate ones are strong, right?
Yep.
And what are those oxidized only?
They oxidize primary and secondary alcohols, but they oxidize primary alcohols to carboxylic acids. It's all in the chapter 12 guide. You could use either one for the ketone. You could do the PCC or the SORN.
So PCC and scoring don't work for what?
They don't turn primary alcohols into carboxylic acids. They only go up to aldehydes. No, just in general, like, okay. If you have a weak oxidizing agent, you'll go from a secondary alcohol to a ketone and then a primary alcohol to an aldehyde. But if it's strong, the ketone stays the same, but the primary alcohol goes to carboxylic acid. Okay, so this is asking for the correct structure of benzyl alcohol. Yeah, it's number 2 because,
It's not a phenol alcohol.
yeah, and a phenol alcohol would be,
One.
yeah. So phenol is when it's directly attached to the benzene ring, and then benzyl is when there's an extra in between. Okay, so more chapter 12. It's asking for product B of the total reaction. So what are we starting with? Yes, we're starting with a ketone, and then what strength of agent is NABD4? Yes, reducing. Is it weak or strong? It's weak. And what do we use for ketones? Yeah, we can use any. So this reaction is going to work, right? Yeah. So what does it turn into?
Second one.
Yeah, it would. And how do you know it's the second one?
I wanted to say just by looking at it, but I guess like, oh, because the D adds to the C, and then the oxygen, then the oxygen just gets protonated by whatever water or acid or whatever.
Yeah. So in the first step, when you're reducing the carbonyl, you're adding a hydrogen to the carbonyl. So we have this ketone right now. When we have the NABD4, it's basically just a D- going in and attacking. So now you have an alcohol with a D attached to it. Oh, well, actually an alkoxide because we haven't protonated yet. So the product of A would be this alkoxide. And then after we add water to protonate this ion. So it just turns into a normal alcohol, but the D stays where it was. You just have to know that the protonation and reduction steps are separate. Okay, and then this one, Do you guys remember the condensed formula functional groups?
On some of them.
Okay, so what functional groups do we have up here? Yeah, we have a ketone, an ether like this. That's an ester. How do we know it's an ester? Yeah, because it's CO2 and then R on either side. So we have a ketone and an ester, and then what do we have on the product side?
2 alcohols.
Yeah, you have 2 alcohols. So you reduced both. Yeah, so you reduce both the ketone and ester, so we need a strong agent. And what's the only strong agent here?
Number one.
Yep. Yeah. Wait. Is that the right amount of carbons? Yeah. So ketone and ester both gone, reduced to alcohols.
How does the carboxylic acid on the side look like in the condensed form?
CO2H. R. Okay, now we have alcohol synthesis. And what reaction is this? Yeah. And then is it mark or anti? Yeah. So what side is the alcohol going to get added to? Yeah. So the top or bottom of the alkene. Okay. And then which answer choice does that? Yeah. Oh, okay. I like this problem. I also wrote this one. Okay. Wait, did you have a question? No? Okay. So I'm asking you to provide a reasonable synthetic strategy for the synthesis of trans 1,2-cyclohexane diol from cyclohexene. So what does cyclohexene look like?
It's a hexane over 1 alkene.
Yeah. And then what's the final product?
Both of the carbons that's on the pie is gonna be alcohol.
Yeah, and it's trans, so we're trying to get from that to this. So how do we do that?
You do an epoxide,
You can. So let's start with an epoxidation. What do we use for that?
MCPA.
Yeah. And then that gives you an epoxide. Okay, now what?
NaOH.
Yeah, so what reaction is that called? Yeah, we can do base or acid catalyzed because, yeah, they're the exact same subs. Okay, yeah, I don't know how to say they're equally, yeah, they're equally substituted. Okay. So we can do a base catalyzed. Like H3O over H2O. Or maybe just, I don't know, maybe just H3O on its own.
BR2 and then.
BR2 would give you something different.
And like H2O afterwards.
That would be for making a halohydrin.
No, but like turn the
Oh.
BRs into alcohols.
Oh, I see what you mean. I guess so.
Yeah,
Okay, so wait, say that again. What would you use?
BR2 and then I forget what turns them into alcohols. Is it NaOH?
Yeah.
It attacks the fat and turns it into
That should work, yeah.
Yeah, and that would be trans as well, right? BR2 and then AOH.
I'm not sure if it would be trans, because,
Because doesn't BR2 add a anti or?
yeah, they do inversion, but if you have like two bromines, it's gonna be separate attacks. So it's not necessarily gonna be trans, like there's gonna be an inversion there, but it might not be completely trans to each
Well, I
other.
know they add on the opposite side.
Yeah, but the opposite side might not be the trans product.
For a base catalyzed, whatever.
Yeah,
So do we only ever use NaOH? Like there's no other.
I mean, there probably is. I haven't seen
That's the
anything
one,
else.
just for example, I don't see NaOH.
Yeah, exactly.
Okay.
Yeah, NaOH is good enough. Okay, so the easiest way to get from an alkene to a trans diol is to make an epoxide and then break it. Because anytime we break an epoxide, it's gonna end up trans. Okay, so this one, we're trying to name something that has some ethers on it. So what's step one of IUPAC? Yeah, so what's the parent chain? Yeah, so one. So we have hexane, and then what are our substituents? But as a substituent, diethyloxy? Yes, diethoxy, because as a substituent, ethers are alkoxy, and then the alk is whatever is attached on this side. So these are both ethoxy, so we can just do diethoxy. And then what numbers is each ethoxy on?
1,3
Yeah, so what's the final name?
1,3 diethoxy.
It's.
Yeah, that's all. Okay, now we have this one. So we have an alcohol, and then what's this? Yeah, and what does this protecting group do? With
A halogen.
which halogens?
Happens to be a chlorine.
Yeah, so we're just gonna replace the alcohol with the chlorine, which is answer choice.
Does the protected group like keep, what's it called, stereochemistry also? Or
This one, I think it inverts.
that one hurts?
Yeah, but it's also at the end, so it doesn't matter. Wait, let me Google that. Yeah, I think ZnCl2 inverts. Okay. Yeah,
I'll take it.
was there a question?
No, it was about the inversion, but it
Oh.
doesn't matter, it's terminal anyway, so.
I'm pretty sure it inverts.
Okay.
Okay, so how do you identify what a tosylate is?
Alcohol attached to it.
Yeah,
So. It can show us all of them.
yeah, I can
I know my students, that's the one.
like show you all of the 8 protecting groups.
Or just like. the two.
Let me just pull it up.
I know my students, the one that has the CL.
Okay, hang on, I have a lot to dig through here. With this. Wait, what was I looking for? Oh, yeah. Okay, so this is all the sulfonate protecting groups. As you can see, it's in Canvas, so you can look at it at your leisure. But it basically just changes based on what's attached. So you can see the green thing changes and the green thing also changes in the name. So that's how you're gonna identify these. You're gonna look at what of the green things is attached to the alcohol. And where was I? I was here. Okay. So what group is attached in a tosylate? What does the tosyl group represent?
Has a ring.
Yes, it has a ring. Yeah.
I have a chlorine in the beginning. And then.
Yeah.
Chlorine leaves and gets replaced by oxygen.
So the chlorine would be here, but in this case, it's replaced by other stuff.
Yeah.
So what do we look at? We look at everything else, right?
So it's one.
Is it?
She circled it. Like subconsciously you're telling us the answer.
I don't know. You tell me. Is it 5?
Because the methanol just like kind of just like.
Yeah,
right
because
up in
we have this. Y- Yes. Yeah, it's 1 because when you have a tosyl group, it's just a phenyl with a methyl attached to it. And you basically just have that phenyl with the methyl attached to the SO2 Cl backbone. So we have the SO2 part, and then we know the Cl gets replaced when we actually use it as a protected group. So in this case, we protected a methanol and we added this giant thing to the methanol, and then the Cl just is gone.
What's TBN?
Tert-butyl dimethylsilate.
What do we use it for?
Protecting group. It's the same as these, basically.
As these?
Yeah, it does the same thing, kind of.
You know, where to recognize it,
Yeah.
how it looks also.
So I saw one problem he included where he was like, where you had to actually know what the structure was. So he was like, oh, we gave this, and then he did the reaction. Instead of abbreviating it as like OTBDMS, he actually drew it out.
I mean, it's easy with the church beetle, right?
Yeah, but there's some similar ones. I just know them. It's fine. Okay, so this one we said was
Sheet that
1.
you just showed us also.
Huh?
Is like the structure of it on that sheet that you just showed us also.
Oh, I don't remember. Let's see. Oh no, it's gonna reload. Never mind. Cool. Okay, this problem is also good. So we're trying to synthesize this through Grignard reactions. So this drawn out in bond line is 1, 2, 3. And then we have a phenyl because C6H5 is a phenyl. And then we have an alcohol. So we have all these answer choices, and we did a Grignard with them and are trying to get this product. So I'm going to give you guys some minutes to do this on your own, and then you can give me an answer.
This is really cool.
This problem?
No, we're doing like working analysis.
Yeah, it's really fun, isn't it? Do you need more time? Or are we done? Yes, no? Still need more time? Yes? Okay, thank you. Okay, do you want a marker to draw it? Yeah, eraser markers, take a side. If you can try and pull it up, like yeah, I just never try. Yeah, it never goes up. I can. I bought new ones.
But also like
So we start with this. We'll use this. It's gonna come inside this. Thinking.
I think it's a.
Is it really trying to- Funny thing is, it's only thought I see anything you come up here.
Little backstab.
Yeah, so that's.
Everyone's add,
Well, I just think that like if I want to attack a primary. That's always that makes sense. But mine just made a weird.
Yeah, where did that come from?
I've read it somewhere.
Hydrohalation is more common.
Mhm. Yeah. Okay, you are really close.
H2O, but yeah.
Okay, you're very, very close, but this would give you.
It's just this that like it's
Yeah,
weird.
so basically the bromine, you can just cut this off and then like this bond stays, but it's now attached to the carbonyl.
Yeah.
So instead of getting that extra methyl coming from the carbonyl,
Mhm.
you kind of push it over onto the actual like substituent. So we want the methyl coming from the carbonyl.
Oh, okay.
To do that, we should replace this H with a methyl.
Mhm.
So we can have this in the end.
Okay, and that would be. Okay, so that would just be A then.
Yeah,
Yeah, that would be A.
nice.
Okay.
Can I have the cat? Yeah, please do applaud. That was lovely. Okay. So his thought process was to I don't know, it was just to add this as a Grignard, but it was the wrong Grignard. So
But you still have the right answer.
no, no, we can judge. Okay, so in order to get this product, the easiest way is to just start with 2 out of 3 substituents. So we have a quaternary carbon in the final product. So the easiest way is to start with a ketone with 2 of the existing substituents. So you could start with like this, and then add this as a Grignard, or you could do the opposite thing, this, and then add this methyl as a Grignard. So knowing that, yes, thank you, it is A, because A is the only one that starts with like the ketone with the 2 substituents on it, the 2 right substituents. Like these 2 are aldehydes, so you wouldn't get that quaternary alcohol or tertiary alcohol in the end product. You could, yeah,
I could be tripping, but is it like an SN2 like reaction? Does it kick off the bromine or is the bromine just kind of like?
no, the bromine was never like attached. So remember when we do a Grignard with like MGBR? Okay, well, this is like pre-Grignardification, like we haven't added the magnesium yet. Yeah, but it just is normal, like with an MGBR.
Okay.
How do you do the first one?
Huh?
How do you do the first one?
So it starts with the ketone with the 2 right substituents. So the final product has 3 substituents. And this one, the ketone has the methyl and the phenyl already attached. So all we have to do is add this chain. So I was like, oh, you can just make like this product, you can just start with as the ketone and then like add this as a substituent.
So you're like literally putting a puzzle.
Yes, exactly.
I have a question about this one.
Probably like this, but not written out in condensed formula, probably in bond line.
Well, I got something like this in there.
Oh, then it's probably gonna be on the test. Yeah.
Some of our tests.
I'll find out on Friday.
Oh, we all will.
Okay, cool. So the next one, we're reacting 2-hexanol with PCC. So 2-hexanol is what alcohol?
Secondary.
Yeah, it's secondary. And then what happens when we give a secondary alcohol any oxidizing agent? Yeah, it just turns into a ketone. So what answer choice gives you the right ketone? Okay, C. We all agree on C? Yeah, it's the only ketone. The rest are CO2, which is not what we're looking for.
Is that written somewhere? I know it's written. Is it on the SI sheet?
What is written?
The condensed forms.
Oh, it's in the chapter 12 answer key. A lot of stuff's in the chapter 12 answer key, so I would suggest looking at it. So we have more Grignards. So what are we starting with? What functional group is that? Yeah, it's an ester. And what happens when we give an ester a lot of Grignard reagents?
break.
Okay, yeah, the cyclic ester is gonna break, but you're gonna add the Grignard twice because one time you have a leaving group, and then the second time it's gonna add, like, it's adding to a ketone. So what's the first step? What's the product of the first addition? There's a lot of whiteboard for you to draw it on. Eraser
Can I erase that
markers.
thing?
Yeah.
Activism and all that stuff.
Yeah,
That's Spanish.
yeah.
What's more?
Activism canceled.
Cancel. I just have to do the first part?
Or you could do the whole thing if you want.
I'll do the first part and I'll let Ivan do the
Oh,
second
yeah, of
part.
course. We love some teamwork.
I'm not gonna have enough space, I just realized. Okay, so, and. So this would attack this, right?
Yeah.
This here. Damn, we have to open this up.
Just put the line. Just put the
I know,
line.
but like I suck at doing it.
Just put the line, it's not that hard.
I'm not an artist.
You don't have to be an artist.
Just breaks the line.
Yeah, literally just erase the bond.
Oh, hey, okay. Can I just do that?
Yes.
Oh, wait, I can keep this actually. And then erase this one. Attach. Can I do that?
Yeah, whoa, okay. Yeah. Yeah, that's fine.
And then it does the same thing.
Okay, wait. So we have an extra lone pair on the oxygen right now, right? Is it gonna do anything? Is it gonna potentially come back down?
Yeah, well, it came back down already.
Oh, you drew it. You could draw the full version. Thank you.
All right, so then it's gonna break it again. So we're gonna get a second one.
Yeah,
Okay, and then this will get oxidized. Correct?
yeah. And then what happened to the other oxygen on the bottom? Yes, perfect. So whenever you see a cyclic ester, or an ester in general, you know you add the Grignard twice to the carbonyl. If you have a cyclic ester, you add it twice, and then the leaving group is gonna leave, but it's not gonna completely leave the molecule since it's cyclic. So it's just kind of unfold. So we added it twice to the carbonyl. Remember, this alcohol is the one that left as a leaving group, and then you have two additions here of the Grignard. Then it gets protonated, and then that's your product. So we ended with a tertiary alcohol. And then what answer choice? Yeah. Nice. Okay, benzyl methyl ether. Which one is it?
Oh, wait, yeah, you're right. It's 30 minutes. That's all.
Yeah, because you have the benzene with the carbon in between, and then also the methyl on this side. So yeah. You have more alcohol synthesis. This reaction is,
Hydroboration.
yeah, what's funny about hydroboration oxidation? Yeah, and then what else? Mhm. So which answer gives you a net anti-Markovnikov and syn addition? Yeah, it's 3 because the alcohol is on the least substituted side, and also the hydrogen is syn to the alcohol. So the alcohol and the existing substituent are going to end up trans. Okay. So anti-Markovnikov hydration of a double bond occurs when it reacts with what? Yeah, because we did that like 2 seconds ago. Okay, which reaction can do this? Yeah, and why not acid catalyzed hydration?
Because that leaves it open to rearrangement.
Yeah, and you have a quaternary carbon, which would do a methyl shift. There was no methyl shift, so it couldn't have been acid catalyzed hydration.
What's A, would it be a methyl?
Yeah, if it was A, the answer would also, it would be this, because this would have like done a rearrangement with the carbocation.
What was the revision for H2?
Okay, so we have oxymercuration, demercuration. It's Markovnikov, so what do we look for?
Most substitute gets the OH.
Yes, and that's answer choice. Yeah. Why are there so many alcohol synthesis? I'm gonna skip this. I think we just did this one. So, what protecting group is that?
Oh, actually, no, that's not.
It's not Sako, no.
It is.
That's not,
Yeah, it is. It's methyl because you have this SO2Cl, which means you have like a sulfonate protecting group, and then this thing attached to it is a methyl, and methyl kind of sounds like methyl, so we know it's going to be a methylate, and it also tells you that in this intermediate. Yeah. So what does a sulfate protecting group do to stereochemistry?
it keeps it the same.
Oh, no.
Yeah, it keeps it the same. Then what inverts it? Yeah, okay, but which protecting groups do an SN2 and inverts it? The what?
Whatever. BR.
Yeah, the PBr3 or the actual Sokol do it.
That's the top of the other one, I would say.
Yes.
So you said the PBr3 and Sokol is the one that inverts.
Sokol 2, not SO2Cl.
Yes, okay. Sokol,
Yeah.
Okay.
Those are the only ones that invert, PBr and Sokol.
For the most part.
Check the chapter 11 guide. What happens if you just have what? Like-
SOCL.
Then you just replace the alcohol with the Cl with inversion.
Also CnCl2 and PCl3, those.
Yeah, but he never uses PCl anything, so. Okay, so we have the methylate, and then the stereochemistry we know is the same. So we have a wedged alcohol. And then we have NaI over ethanol. What reaction is that? Yeah, it's SN2, and that does what to stereochemistry? So what's your final product? Yeah, it's 2, because we know we're gonna end with an iodine replacing the alcohol, and it also inverted. That's only in 2. Okay, this is literally the same thing. So let me see if I have anything else. Okay, so if we have cis-2 butene that reacted with MCPBA, what's the final product? Cis-2 butene looks like this. Yeah, it's 1 because the substituents started cis and then they ended cis. And if we had trans-2 butene, what would the final product be? Yeah, they're trans. Okay. The second to last one. The second to last one, I don't think is important. So what is the last one? And it's asking you to prepare ethoxycyclopentane via Williamson ether synthesis. So what does ethoxycyclopentane look like? It is a ring, yeah. A ring of how many carbons? Yeah. So, whoa. We have a cyclopentane, and then we have an ethoxy coming out of it. We know it's an ethoxy because this substituent is an ethyl. So cool. What would you use to get this with Williamson ether synthesis?
Would it be intramolecular?
No. Is there, no, yeah. If like the oxygen was inside the ring like that, then yes, but it's not.
That was the BR.
Yeah, so what would you put the BR on?
No.
Yeah, so you'd have an ethyl bromide. And then what would the nucleophile be? Yeah, the ring with what? With an OH?
Yeah.
Yeah, with an OH. The ingredients for Williamson ether synthesis are an alcohol, a base, and an alkyl bromide. So yeah, we need an alcohol.
This is an essential like.
Yes. And then, what was the third ingredient that I just said? Yeah, we need a base, a strong base, NaH. So the base just goes, deprotonates it, then we get a good nucleophile. Then it just goes and attacks, and then you end with this.
See, chemistry's not hard.
Yeah, chemistry is really fun. But anyways, time is up and we finished this, so that's great. I won't be posting an answer key, so like get the answers from your friends or something. Or you could watch the recordings, but if I wouldn't want to sit through 2 hours, but if you do, then go ahead. But yeah, sorry, no answer key, and then this is not going to go on Canvas at all. Oh yeah, good luck on your exam.